So these videos are going to look at types of reactions. So previous videos looked at how to balance equations of reactions and what reactions are. Now we're going to look at different types of reactions that you may experience in different scenarios. So just a little refresher. So one of the things we're going to look at first are acid-base reactions. And so these involve ions. So remember, ions are atoms that have lost or gained one or more electrons. And specifically, what we're going to be looking at are hydrogen ions and hydroxide ions. So pure water has equal amounts of these guys. So you can see they're written as H plus and OH negative. So water itself is non-ionized. So it's a full molecule with the two hydrogens and the oxygen. And it goes back and forth between that and the ions. Now, pure water is going to have equal amounts of these, so that's why it has what we would consider a neutral pH. And you can see here, we end up getting the hydrogen ion, the H plus, because that hydrogen gets separated off of the water molecule in this case, and the electron gets donated to the hydroxide molecule. And then the hydroxide molecule, it is OH negative, and that is because it has received that donated electron from the hydrogen molecule. And so it's going to be that hydroxide molecule that is negative. These two ions, so the hydrogen ion and the hydroxide ion, are the two that we're going to be looking at as we talk about acids and bases, what they are, and then acid-base reactions. All right, so we're going to take a look first at acids. So acids are found in all of the products that you see here. Acids are any chemical that donate hydrogen ions. So they are going to donate those H pluses, and so they don't have to be water. Water is just one example of where you can get these hydrogen ions. They can be any chemical that donates hydrogen ions. And the thing is that where acid or acidic comes from, acid means sour in Latin. And so things that are acidic are things that taste sour to us. So if you think about things like a lot of the citric fruits, they do taste sour. They may have more sugar in them, like an orange, but they still are going to taste more sour than something like an apple. The sourness of pickles, that's coming from acidic compounds that are in those pickles. The acid that we're looking at here is in the cleaning product, and then there are acids in soda. That's one of the reasons why you are told by your dentist to not drink this. Specifically, the acid in soda is carbonic acid, made by the carbon dioxide that's dissolved in the soda to make the carbonation. So what are some examples of other acids? So a lot of people know hydrochloric acid. That's what we consider a strong acid. And we'll talk about what strong acids and weak acids and bases are here in a little bit. Vinegar. So that's actually the acid that's in pickles. That's acetic acid. And I mean, there are lots of them. There's lactic acid. So that's one that's found actually in our cells after you do a long workout. That's what makes your muscles feel sore. So there's lots and lots of different acids. A lot of them do have the name acid in their name. So for example, the one found in these guys down here is citric acid. They are incredibly useful, used in all kinds of different materials. As you can see here, we use them in the manufacture of all of these different materials. And some of them are just straight out used as their own product. So, like I said, you've got the acetic acid, the vinegar that's in pickles. And we've got acids that are in these cleaning products, like what we find here in the toilet bowl cleaner. So, so acids are any chemical that's going to donate a hydrogen ion for the reaction. The opposite are going to be bases. Bases are anything that accept a hydrogen ion. So these are things that are going to accept that hydrogen ion, and we'll see how that works here as far as the reaction goes. Typically, we'll see bases have a higher concentration of hydroxide ions and hydronium ions, so we'll see those. These guys are characterized by bitter tastes. So the one that you might be familiar with as far as tasting is baking soda. So I don't know how many of you have on purpose tasted baking soda, but it does have a slightly bitter taste to it. And these have a slippery feel. So think about things like soaps. So that's what you're seeing here. Soaps and other cleaning products, that is mainly what we're looking at as far as bases. And this is because the base is actually taking your skin oil and making it into soap. I know that sounds really weird, but that is what's going on. So the base is actually taking those skin oils and turning them, transforming them into a soap material. That's why you get that slippery feeling. It's actually creating soap. So for example, if you've ever gotten like bleach, because bleach is a base, if you've gotten bleach on your hands, that slippery feeling, it's because it's making soap. And then it's actually starting to do damage if you leave it on for any longer amount of time, because it's going to actually start pulling hydrogen ions and so forth out of your skin. So these are often what we consider cleaning products. So, you know, bleach, ammonia, that's why this guy, the Drano, is here. Our soap products and so forth are going to be in the base area. All right, so taking a look here at now the pH scale, we can see more examples of the acids and bases. So again, acids are any material that can donate protons, and bases are anything that accept protons. And so because of that, what we see is when we look at an acid, we get a higher concentration of those hydrogen ions or protons, sorry. And so if you look up here at the key, we've got hydrogen ions. You might hear me call those protons because that's basically what they are. They are just the proton, just the nucleus from a hydrogen. You've got water and you've got hydroxide ions. And so since acids are materials that donate those protons or hydrogen ions, you're going to see more of those hydrogen ions in that material. And so we saw some examples of these guys already, but here's some other ones. So coffee, beer, soda, stomach acid, they are all on the acid side of the pH scale. So you can see that pure water is at 7. It's neutral. So that's what we mark as the neutral point on the scale is 7. So as you go lower on the pH scale, you become more and more acidic. So as you go lower, you have more and more hydrogen ions. So as we already talked about, these guys are going to be sour. They are corrosive, so they do break down things. And you've experienced this with your stomach acid. Not just it doesn't just digest your food, but if you've ever been sick, you vomited, you've experienced the digestive properties or the corrosive properties of your stomach acid. You can see it's quite low on the pH scale because after you vomit, your throat hurts, not just from, you know, the actual physical part of it, but your throat will burn, and that is because of the acid. The acid's actually doing damage to the tissue in your throat. You can actually make that burning sensation go away if you're capable and able to keep anything down by consuming a base. So bases are the higher end of the scale because these guys can accept protons or hydrogen ions, and so they have higher numbers of hydroxide ions, so the little guys that are just oxygen and hydrogen. And a common one for that would be something like baking soda. So we use things like baking soda, Mylanta, Tums. They all contain the same sort of material that are up here on this slightly higher part in the base section because they can accept those hydrogen ions and neutralize the acid. And we'll talk about how that works in a second with the acid-base reaction. And as you can see, like I mentioned before, these are mainly cleaners. But even our blood is slightly basic. So we actually tend to hang around right here in the neutral area or in the neutral zone as far as the pH scale goes. So let's think about this pH scale as far as if we had a cup of lemon juice. So you can see lemon juice is actually more acidic than our stomach acid. What would happen if we had a cup of lemon juice and we added a cup of water to it? What would happen to the pH? So lemon juice again's here, and if we added water to it, would the pH go down or would it go up? And so if we do just a little drawing here, so we have our cup of lemon juice, and inside of that cup, when it's just lemon juice, think about it like this. Here are the hydrogen ions, right? That's making the lemon juice sour, and it's low on the pH scale, so that means there's a lot of them. Now, if we're using water, water is here at 7, right? So it's not going to have any hydrogen ions in it, really. And so now our cup is going to have twice the volume. I'm going to draw the cup a little bit bigger now. So it's going to have twice the volume because we've added another cup in, but we haven't added any hydrogen ions because water, pure water, has no hydrogen ions. So since it hasn't changed the number, what we've changed is the concentration. So they're more spread out. And pH is all about the concentration, the number of them. And so if we add a cup of water to a cup of lemon juice, the pH is going to increase. It's going to move towards 7 because you're actually spreading out those hydrogen ions. You're decreasing the concentration of hydrogen ions. I know that sounds weird. But as you decrease the number of hydrogen ions, the pH increases. Okay, so you can see here, the more, that's not what we want, but the more hydrogen ions you have, the more acidic you get. The more hydroxide ions, the more basic you get. Okay. So you may have heard about strong and weak acids. So I just wanted to mention those real quickly. So what these are, they are acids and bases, but it's all about how they interact with something like water. And so here you can see that the cartoon, they are mixing hydrogen chloride in with water, and hydrogen chloride does work as an acid. It's going to donate protons, but it is considered a strong acid because it's going to completely ionize. So what does this mean? Well, this means that if you look in here, every single one of these chlorines has given up its hydrogen. So that's what we mean by completely ionize. So all of the molecules give up their ions. So if it is an acid, all of the acidic molecules give up their hydrogens. If it's a base, all of the basic molecules are going to accept protons. So everybody in a strong acid is going to do, it's going to give them up. Everybody in a strong base is going to accept them. This is a little different when you look at a weak base or acid. So acidic acid, or acetic acid, which is vinegar. This is a weak base, or I'm sorry, a weak acid. And the reason why is it's still going to donate a proton, or hydrogen, so it's still going to give up this hydrogen right here. It's going to become an acetate ion, and we're going to get hydrogens donated out. And so some of them are going to become what they have listed here as hydronium ion. Basically, there's still hydrogen ions running around. But the difference is, if you look, this is the only acetate ion that's in here. All of these other guys still have their hydrogens attached. This is what we mean by not completely ionizing. So only 1 out of the 4 of these acetic acid molecules actually ionized, actually gave up their hydrogen. And so that's what makes the difference between a strong and a weak acid, if you hear that. All right, so let's take